The Americans took one look at this aircraft, called it plywood and glue, and refused to build a single one. 3 years later, they were begging Britain for as many as they could get. That's not folklore. That's not internet mythology. That's documented history, preserved in rejection letters and procurement records, and the quiet humiliation of officials who discovered their absolute certainty had been absolutely wrong. The story begins not with the rejection, but with the vision that made rejection possible. In 1938, Geoffrey de Havilland, founder of the de Havilland Aircraft Company, a man who had been building aircraft since before the First World War, began contemplating a design that would strike most aviation experts as deliberately perverse. While every other manufacturer in the world was racing to master aluminium construction, de Havilland proposed going backward. He wanted to build a fast, twin-engine bomber primarily from wood. This was not desperation, this was calculation. De Havilland understood something that escaped the aluminium evangelists, who dominated aviation thinking on both sides of the Atlantic. Wood was not simply an inferior substitute for metal. It was an engineering material in its own right, with properties that could be exploited by designers who understood its nature. The company had spent decades refining techniques for stressed wooden monocoque shell construction. Techniques that created airframes simultaneously lighter and stronger than their metal equivalents when properly designed. The proposal that emerged by October 1939 was radical enough to make the British Air Ministry nervous. A bomber with no defensive armament whatsoever, no gun turrets, no gunners. Just a two-man crew in a wooden airframe, relying entirely on speed to survive. The idea was simple in concept and audacious in execution. Build an aircraft so fast that enemy fighters simply couldn't catch it. If you could outrun anything sent to intercept you, why bother carrying the weight of guns and ammunition and the men to operate them? The Air Ministry's resistance ran deeper than mere skepticism. Officials had genuine concerns about allocating scarce resources to an unconventional design when conventional aircraft programs were already straining British industrial capacity. The Battle of Britain was approaching, though no one knew its timing yet. Fighter Command needed Spitfires and Hurricanes in numbers that factories struggled to produce. Bomber Command was demanding Wellingtons and Hamptons and the new four-engine heavies that were still on drawing boards. Into this environment of desperate priority setting came de Havilland with a proposal for an unarmed wooden bomber that defied every assumption about what combat aircraft should be. But de Havilland had allies. Air Marshal Sir Wilfrid Freeman, the Air Council member responsible for aircraft development and production, recognized something in the proposal that resonated with his own thinking about bomber survivability. Freeman understood that defensive armament had become a kind of institutional comfort blanket, a way of reassuring crews that they could fight back against interceptors, even when the mathematical reality suggested that turret guns rarely saved bombers from determined fighter attacks. The weight of turrets and gunners and ammunition degraded performance significantly. If an aircraft could be made fast enough to simply outrun fighters, perhaps that weight could be better invested in speed or payload or range. Freeman fought for the project within the Air Ministry bureaucracy. His support proved decisive. By October 1939, enough officials had been persuaded to issue a contract for a single prototype. Though skepticism remained pervasive among those who viewed wooden construction as a concession to expected aluminium shortages rather than a genuine engineering choice. That prototype, designated W4050, first flew on November 25, 1940. Test pilot Geoffrey de Havilland Jr., the founder's son, took the aircraft up from Hatfield Aerodrome and discovered that his father's calculations had been conservative. The Mosquito wasn't just fast, it was faster than nearly everything else in the sky. The test program revealed performance that exceeded even the designer's expectations. Speed trials showed the aircraft could exceed 400 miles per hour, faster than the Spitfire, faster than any contemporary bomber, faster than most fighters. And this was before refinements that would push later variants even higher. Before the PR Mark 16 would achieve 415 miles per hour, with a service ceiling exceeding 38,000 feet. Word of the aircraft's performance began circulating through aviation circles. And in the spring of 1940, General Henry Hap Arnold, commanding general of the United States Army Air Corps, visited Britain to assess the state of British aviation and identify technologies that might benefit American forces. During that visit, Arnold witnessed a mosquito demonstration that left him genuinely impressed. He watched the aircraft execute an upward roll on a single engine, a feat that demonstrated a power-to-weight ratio few contemporary designs could match. Arnold returned to America, convinced that the mosquito represented something worth serious study. He personally delivered complete blueprints and technical data to American manufacturers for evaluation. If American industry could produce this aircraft, it would dramatically expand Allied capabilities. American factories, once mobilized, could achieve production scales that British workshops could never match. 5 of America's most respected aircraft manufacturers received that technical data: Beech, Curtiss-Wright, Fairchild, Fleetwings, Hughes. These weren't marginal operations or backyard experimenters. These were the companies building America's air forces, the engineering establishments whose assessments shaped procurement policy, whose verdicts carried genuine weight. Every single one rejected the design. And they didn't hedge. They didn't suggest modifications or express cautious reservations. They condemned. Beechcraft's formal evaluation stands as the clearest record of American contempt. Their assessment stated, and the absolute confidence in this language deserves attention: "This aeroplane has sacrificed serviceability, structural strength, ease of construction and flying characteristics in an attempt to use construction material that is not suitable for the manufacture of efficient aeroplanes." Read that again. Beechcraft didn't suggest wooden construction presented certain challenges that might require adaptation for American production methods. They declared that the entire concept was fundamentally misguided. The material itself was unsuitable. Period. Full stop. Case closed. The other 4 manufacturers reached substantially identical conclusions. All formally rejected the design, dismissing its wooden construction as an act of desperation rather than innovation. The word desperation carried particular weight in this context. The American manufacturers weren't merely claiming wood was inferior to metal. They were suggesting that no rational designer would choose wood unless circumstances forced his hand. The British, in this reading, were building wooden aircraft because they couldn't build metal ones, because their aluminium supply was constrained, their metalworking labour force was depleted, their industrial capacity was exhausted. The mosquito was, in American eyes, a symptom of British weakness rather than a manifestation of British ingenuity. General Arnold found himself in an uncomfortable position. He'd actually seen the aircraft fly. He'd witnessed performance that impressed him. But he was overruled by officials who believed the Lockheed P-38 Lightning would be equally capable of filling whatever role the Mosquito might perform. The P-38 was certainly impressive. Twin engines, twin booms, capable of reconnaissance and ground attack in addition to its primary fighter role. American officials saw no reason to pursue an unconventional wooden design when they had a proven metal aircraft already in production. The comparison revealed a fundamental misunderstanding of what the Mosquito was designed to accomplish. The P-38 was a fighter that could also perform other missions. The Mosquito was something else entirely. A bomber so fast it didn't need defensive armament. A reconnaissance platform that could photograph targets no other aircraft could reach. A design philosophy that prioritized performance over conventional doctrine. But institutional certainty, once established, resists mere evidence. The rejection letters had been written. The verdicts had been rendered. American industry would pursue its own designs, in its own materials, confident in the superiority of its own engineering traditions. The British would build their wooden aircraft alone. While American manufacturers dismissed the Mosquito as unsuitable for efficient construction, de Havilland's engineers at Hatfield were refining the design in ways that would prove its critics spectacularly wrong. The wooden construction that Beechcraft had condemned for sacrificing structural strength was, in reality, an exercise in sophisticated materials engineering that American observers had failed to understand. The Mosquito's fuselage was not carved from timber like a canoe. It was constructed using pressure-laminated techniques that created a wooden monocoque shell of extraordinary strength and rigidity. The structure consisted of two half shells, each built up from multiple layers of materials bonded together under pressure. The outer skins were birch plywood, selected for its consistent grain and excellent bonding characteristics. Between those plywood skins lay cores of balsa, chosen for its remarkable strength-to-weight ratio. The balsa was lighter than any practical alternative, while providing the core stiffness the structure required. The whole assembly was bonded with casein glue, a milk protein adhesive that formed joints stronger than the wood itself when properly cured under controlled conditions. The two fuselage halves were built in female moulds, the layers of plywood and balsa laid up carefully, the casein glue applied, the assembly placed under pressure until the adhesive set. Then the two halves were joined along the aircraft's centerline, creating a smooth, compound curved structure that would have been extraordinarily difficult to achieve in riveted aluminium. One technically minded observer would later describe this as quite exotic pressure laminated wooden core and skins. And that word exotic captures something the American manufacturers missed entirely. This wasn't desperation wood, this was engineered wood. The construction technique was closer to advanced composite manufacturing than to traditional carpentry. The stressed skin approach meant the outer surface carried structural loads, eliminating the need for heavy internal frameworks. Every element of the structure contributed to strength and rigidity. The compound curves provided inherent stiffness. The sandwich construction, plywood, balsa, plywood, created a structure that resisted buckling better than single-layer materials of equivalent weight. The result was an airframe that weighed substantially less than a comparable metal structure would have weighed, while meeting or exceeding the strength requirements for high-performance military operations. The weight saving translated directly into performance: more speed, more range, more payload capacity for a given amount of engine power. But the engineering sophistication extended beyond the basic structure. The Rolls-Royce Merlin engines that powered the Mosquito required their own adaptations to work safely with the wooden airframe. Standard Merlin installations, as used on Spitfires and Lancasters, featured 6 exhaust stubs per engine side. This configuration had become standard across multiple aircraft types, and there was no particular reason to change it for most applications. But the Mosquito was not most applications. The Mosquito used only 5 exhaust stubs per side, and this modification was not a simplification. It was a carefully considered engineering solution to a problem unique to wooden aircraft construction. The fifth and sixth exhaust ports were combined and redirected specifically to prevent exhaust gases from bleeding into the inboard radiators and to protect the combustible wooden wing structure from severe heat damage. The designers had understood that placing conventional high-temperature exhaust outlets near a wooden wing leading edge would create unacceptable fire risk. Hot exhaust gases impinging on wood and fabric surfaces could cause scorching, structural weakening, or outright ignition. So they modified the installation. They solved the problem before it could become a problem. The American manufacturers who dismissed wooden construction as unsuitable hadn't considered any of this. They'd looked at wood and seen primitive. They'd missed the engineering entirely. And then the modification delivered an unexpected bonus. Later Mosquito variants utilized multiple ejector open-ended exhaust stubs that optimized thermal management while providing a performance benefit that no one had initially anticipated. The ejector exhaust configuration actually increased speed by 10 to 13 miles per hour through the thrust effect of the exhaust gases. The hot gases, expelled rearward at high velocity, provided a small but meaningful addition to the aircraft's total thrust. What had begun as a safety modification, keeping hot gases away from wooden structures, had evolved into a performance enhancement. The wooden construction that supposedly sacrificed flying characteristics was driving innovation that made the aircraft faster than it would otherwise have been. The evidence was accumulating. But evidence alone rarely defeats institutional certainty. The American manufacturers had rendered their verdicts, and American procurement policy would follow those verdicts regardless of what was happening at Hatfield or in the skies over occupied Europe. Meanwhile, production of the Mosquito was expanding beyond Britain itself. By the end of July 1941, plans were well advanced to establish manufacturing in Canada, taking advantage of de Havilland's existing subsidiary in Toronto. This Canadian contribution deserves attention that it rarely receives in Americanized histories of the war. De Havilland Canada, operating from their factory at Downsview, would eventually build 1,032 Mosquitoes during the war years, with an additional 100 produced after the fighting ended. That's over 13% of the 7,778 total Mosquitoes manufactured across the Commonwealth. A substantial contribution from a nation whose aviation industry is routinely overlooked. The Canadians built multiple variants. Fighter bombers designated FB-6, bomber variants marked B Mark 20 and FB-26. Aircraft like FB-26, serial number KA-114, taken on Royal Canadian Air Force charge in February 1945. These weren't experimental curiosities or limited production test articles. This was industrial-scale manufacturing of an aircraft that America's 5 leading manufacturers had declared unsuitable for efficient construction. The Canadian production line at Downsview faced challenges that their British counterparts didn't encounter. Canadian birch differed slightly from British sources. Canadian climate conditions required adjustments to glue curing procedures. Canadian workers had to be trained in techniques that were well established at Hatfield, but entirely new to Toronto. Yet the Canadians adapted, refined their processes, and eventually achieved production rates that contributed meaningfully to total Mosquito availability. De Havilland Australia added their own contribution from facilities in Sydney. The Commonwealth had mobilised behind the rejected design: Britain, Canada, Australia. Factories across 3 continents, turning out hundreds of machines that Beechcraft had insisted sacrificed structural strength, serviceability, ease of construction, and flying characteristics. The irony bears contemplation. Furniture factories and woodworking shops across the Commonwealth were efficiently producing sophisticated combat aircraft, while American industrial experts maintained that the entire concept was fundamentally flawed. And what were those machines doing in combat? Everything. The Mosquito became perhaps the most versatile aircraft of the entire war, filling roles that no single design had ever filled before. The variants multiplied as operational experience revealed new possibilities. Photo reconnaissance Mosquitoes penetrated deep into occupied Europe, photographing targets that no other aircraft could reach and return from. Berlin, Vienna, targets in Norway and Poland and the Balkans. The PR Mark 16 variant achieved a top speed of 415 miles per hour at altitude, with a service ceiling exceeding 38,000 feet. Performance figures that compared favourably with dedicated single-engine fighters while carrying cameras and fuel for missions of vastly greater range. These aircraft operated alone, climbing to altitudes where interception was nearly impossible, photographing whatever they were sent to photograph and returning with intelligence that shaped Allied planning throughout the war. Night fighter Mosquitoes transformed the air defence of Britain. Equipped with airborne interception radar, crewed by a pilot and a radar operator working in close coordination, these aircraft hunted German bombers in darkness that had previously provided immunity. The combination of radar detection, high speed, and heavy armament, 4 20mm cannons and 4.303 machine guns in the fighter variants, made the Mosquito night fighter a lethal opponent. German raiders that had once operated over British cities with relative impunity found themselves tracked, intercepted, and destroyed by aircraft they never saw until cannon shells began striking their airframes. Pathfinder Mosquitoes served with the elite squadrons tasked with marking targets for RAF Bomber Command's heavy bomber streams. These aircraft would dash ahead of the main force, navigating with precision to the target area, and plant target indicator flares that the following heavy bombers would use as aiming points. The accuracy of the entire bombing effort depended on the accuracy of the Pathfinder marking, and the Mosquito's speed and performance at altitude made it ideal for this demanding role. Pathfinder crews were among the most highly trained in Bomber Command, and their aircraft needed to be capable of reaching the target before the defences were fully alerted, marking accurately and escaping before fighters could concentrate against them. Fighter-bomber Mosquitoes executed precision raids that entered legend. Low-level attacks against specific targets, individual buildings rather than general areas, that heavy bombers could never have accomplished. Operation Jericho stands as perhaps the most famous example. On February 18, 1944, Mosquitoes of 487 Squadron, Royal New Zealand Air Force, 464 Squadron, Royal Australian Air Force, and 21 Squadron, RAF, attacked Amiens prison in occupied France. The target was not the prison itself, but the prisoners inside, members of the French resistance, many of whom were scheduled for execution. The plan called for Mosquitoes to breach the prison walls with precision bombing, allowing prisoners to escape in the confusion. The attack went in at rooftop height. Crews pressed their aircraft through heavy flak, delivered their bombs against the prison walls, and wheeled away over the French countryside, while behind them walls collapsed and prisoners scrambled through the breaches. Some escaped. Some did not. The operation remains controversial. Questions persist about whether the raid was requested by the resistance, whether the German guards had time to execute prisoners during the chaos, whether the cost in lives lost during the attack was justified by the lives saved through escape. But the operational demonstration was beyond dispute. Mosquitoes had delivered a precision attack against a specific building, in daylight, at extreme low altitude, in the face of enemy defences. No other aircraft in the Allied inventory could have done what the Mosquitoes did that day. Heavy bombers lacked the precision. Fighters lacked the bomb-carrying capacity. Only the Mosquito combined the speed to survive the approach, the accuracy to hit a specific structure, and the payload to breach stone walls. Similar precision attacks followed throughout the war. Gestapo headquarters in Copenhagen, the Shell House building in The Hague, specific facilities rather than general target areas. Surgical strikes that required an aircraft capable of reaching the target at low level, delivering ordnance with accuracy measured in yards rather than hundreds of yards, and escaping before defenders could organise effective response. And then there was the variant that seemed almost calculated to embarrass the American manufacturers who had condemned the Mosquito's structural strength. The Mosquito FB Mark 18 carried a designation that told part of its story. Tsetse, like the African fly, a small creature with a bite vastly disproportionate to its size. This specialised maritime strike variant mounted a Mollins 6-pounder Class M cannon in its nose. To understand what this means, consider that a 6-pounder is a 57mm weapon, essentially a modified anti-tank gun fitted with an autoloader and installed in an aircraft that Beechcraft had declared structurally compromised. The Mollins cannon carried 25 solid armour-piercing rounds and could fire at a rate of 55 rounds per minute, capable of emptying its entire magazine in just under 30 seconds of sustained fire. The installation required significant structural reinforcement around the weapon mounting, absorption of substantial recoil forces, and precise alignment to ensure accurate fire. The plywood and glue aircraft was hunting submarines with an anti-tank gun. The attack doctrine developed for Tsetse operations demonstrated the tactical sophistication that RAF Coastal Command brought to the anti-submarine war. Pilots would descend in a 30-degree dive from 5,000 feet, aiming specifically at a U-boat's waterline. The geometry was precise and intentional. Strike at the waterline so the 57mm shell would penetrate the pressure hull and cause catastrophic exit damage below the waterline on the far side. A hit above the waterline might cause damage, but a hit at the waterline would create flooding that a submarine's crew could not control. This was not spray and pray. This was precision gunnery from a diving aircraft, requiring skilled crews to deliver accurate fire against a small, partially submerged target while closing at high speed through defensive flak from the submarine's deck guns. U-boat crews were not passive victims. They fought back with 20mm and 37mm anti-aircraft weapons that could destroy an attacking aircraft if the pilot's approach gave them a clean shot. The aircraft that American experts had condemned for poor flying characteristics was being flown with surgical precision by crews of RAF Coastal Command's 248 Squadron. Squadron leader A.K. Tony Phillips and the crews of 248 Squadron flew those Tsetse operations against German U-boats in the Bay of Biscay and the western approaches, and they compiled a combat record that spoke for itself. Their confirmed kills included U-976, destroyed on March 25, 1944. And in one of the most remarkable single-day performances of the entire anti-submarine campaign, a trio of German submarines, U-804, U-843 and U-1065, fell to Mosquito attacks on April 9, 1945. 3 submarines in one day. From wooden aircraft armed with weapons that would have struck American manufacturers as borderline insane. Flight lieutenant crews pressed their attacks through flak, diving toward the waterline, while German gunners threw everything they had at the incoming aircraft. The closing speed gave the submarine gunners only seconds to track, aim, and fire effectively. The Mosquito's speed and maneuverability made it a difficult target even in the final moments of an attack run. The psychological impact extended beyond individual kills. German naval intelligence formally noted that the technical initiative has passed irreversibly to the enemy, a statement that conceded that Tsetse Mosquito had fundamentally altered the tactical calculus of anti-submarine warfare. The aircraft forced German U-boats to remain submerged, even when surfacing would have been tactically advantageous. Accept the reduced performance of underwater operation. Accept the limited battery endurance. Accept the constrained situational awareness of blind sonar operation. Because surfacing meant exposure to cannon-armed aircraft, they couldn't outrun and couldn't effectively engage. The submarines that had nearly strangled Britain's supply lines in 1941 and 1942 were being hunted to extinction by wooden aircraft armed with anti-tank guns. But the Mosquito's versatility extended into even more exotic territory. In 1943, Barnes Wallis, the engineer who had conceived the bouncing bomb that would be used against German dams, developed a smaller version called Highball, intended for use against capital ships, particularly the German battleship Tirpitz, lurking in Norwegian fjords. The weapon required a specialized delivery aircraft, something fast and maneuverable enough to attack heavily defended ships at low level. The aircraft chosen for development and potential operational use was the Mosquito. 618 Squadron RAF formed specifically to operate the Highball weapon from modified Mosquito B Mark IVs. The concept was audacious. Approach enemy warships at extremely low altitude, release a spinning spherical bomb that would skip across the water surface like Wallis's larger dam-busting weapon, strike the ship's hull at the waterline and sink beneath the surface before detonating against the hull below the waterline, where armour was thinnest and damage would be catastrophic. The squadron trained intensively in Scotland, practicing the precise approach profiles and release parameters that the weapon required. Pilots learned to fly their Mosquitoes at 60 feet above the water, barely higher than the aircraft's wingspan, at speeds exceeding 350 miles per hour, releasing the spinning Highball at exactly the right moment to achieve the skipping trajectory that would carry it to the target. As it happened, 618 Squadron never employed Highball operationally against Tirpitz. Other weapons, first tallboy deep penetration bombs, eventually a combination that included Lancasters, would finally destroy the battleship in November 1944. But the Highball program demonstrated something significant about the Mosquito's adaptability. The same wooden aircraft that American manufacturers had dismissed as structurally inadequate was being modified to deliver one of the most innovative weapons of the war. The same airframe that supposedly sacrificed flying characteristics was being flown at 60 feet above frigid North Sea waters in conditions that would destroy lesser aircraft and lesser crews. 618 Squadron eventually deployed to the Pacific Theatre, where they were intended to use Highball against Japanese ships. The war ended before they saw combat, but their Mosquitoes made the journey. Wooden aircraft designed for European conditions, operating in tropical environments thousands of miles from Hatfield. But here's where the engineering story takes a darker turn. The casein glue that bonded the Mosquito's wooden structure was a remarkable adhesive in temperate conditions. In controlled environments, properly cured casein formed bonds stronger than the wood itself. The Hatfield-built aircraft, operating in British and European conditions, performed flawlessly. The tropics were different. When Mosquitoes deployed to Burma, India and the Pacific Islands, they encountered conditions that the original design hadn't fully anticipated. The combination of extreme heat, high humidity and tropical organisms created stresses that tested the limits of wooden aircraft construction. The casein glue, fundamentally a milk protein product, proved vulnerable to the relentless moisture of monsoon conditions. In some cases, the glue softened. In extreme cases, it failed. Wing skins separated from their underlying structures. Fuselage joints opened. Aircraft that would have performed perfectly in England developed structural failures that grounded entire squadrons. The problem was real enough that de Havilland had to develop modified construction techniques for aircraft destined for tropical service. Alternative adhesives were tested. Improved sealing methods were implemented. Aircraft built or modified for Far East service incorporated changes specifically designed to resist the conditions they would encounter. This wasn't a secret shame buried in classified files. The tropical difficulties were known, acknowledged, and addressed. But they reveal something important about engineering reality. The Mosquito wasn't perfect. It was extraordinary, but it operated within the boundaries of materials science as understood in 1940. The American manufacturers who rejected wooden construction hadn't been entirely wrong about the challenges. Wood was susceptible to moisture damage, insect attack, and fungal growth in ways that metal was not. The brilliance of the Mosquito lay not in avoiding these challenges, but in solving them, creating construction techniques and maintenance procedures that allowed wooden aircraft to operate successfully across most of the conditions they encountered. The tropical failures were engineering problems that required engineering solutions. De Havilland found those solutions. Later production aircraft incorporated improvements. The Mosquito's operational record in Burma and the Pacific ultimately vindicated the basic concept, even as specific aircraft suffered failures that metal construction would have avoided. American critics would later point to the tropical difficulties as vindication of their original skepticism. But this missed the larger picture entirely. The Mosquito operated successfully from bases across the world, in conditions ranging from Arctic cold to tropical heat, from desert dryness to monsoon downpours. Some aircraft failed. The vast majority performed magnificently. The overall record demonstrated that wooden construction could work, with appropriate attention to materials, manufacturing, and maintenance. And throughout all of this, the precision raids, the submarine hunting, the photo reconnaissance, the pathfinding, the night fighting, the tropical adaptations, the Mosquito maintained a loss rate that validated everything its designers had claimed. With a top speed above 400 miles per hour, Mosquito crews could outpace any contemporary fighter sent to intercept them. That wasn't propaganda or manufacturer's optimism. That was measured performance, validated repeatedly in combat operations where Mosquitoes escaped interception through pure velocity. The lightweight construction that American manufacturers had dismissed as sacrificing structural strength was producing aircraft that were harder to shoot down than their metal contemporaries precisely because they were fast enough to avoid combat they didn't choose to accept. Then came December 7th, 1941. Pearl Harbor changed everything about American strategic calculations. Suddenly at war across two oceans simultaneously, suddenly facing requirements that had seemed theoretical just weeks before, suddenly discovering that institutional certainties might need reconsideration when circumstances demanded capabilities that existing programs couldn't provide. Days after the attack, a telegram arrived at de Havilland. The USAAF officially requested a Mosquito for evaluation. The exact same aircraft design they had previously declared unsuitable. Built from materials they had condemned as inappropriate for military aviation. The experts at Beech, Curtiss-Wright, Fairchild, Fleetwings and Hughes had rendered their verdicts with absolute confidence. Now their government was quietly asking to borrow what those experts had rejected. The British noticed the irony. Difficult not to. For 18 months, American manufacturers had insisted that wooden construction sacrificed structural strength, serviceability, ease of construction, and flying characteristics. Now, with America facing wars on multiple fronts, with production requirements expanding exponentially, with the urgent need for high-performance reconnaissance aircraft becoming desperately clear, Those same characteristics looked rather different. The mosquito hadn't changed. Only American circumstances had changed. And changed circumstances were forcing a reconsideration that institutional pride had previously prevented. The initial request was just the beginning. Through reverse lend-lease, the mechanism by which Britain supplied war materials to the United States, reversing the usual direction of Allied aid flows, the USAAF eventually ordered 120 mosquitoes specifically for photographic reconnaissance purposes. 120 aircraft of a design that 5 American manufacturers had unanimously rejected. Aircraft built from materials those manufacturers had declared unsuitable for efficient construction. The procurement process itself underscored the reversal. Canada had been producing mosquitoes since 1942, and early Canadian-built airframes, designated F-8 by the USAAF, found their way to America for testing and evaluation. The Americans were receiving their first mosquitoes from a Commonwealth nation whose woodworking industries had succeeded where American metal expertise had refused to even attempt the challenge. By 1944, British-produced mosquitoes were flowing to American units in meaningful numbers. The USAAF's 25th Bomb Group operated mosquitoes for reconnaissance and specialized missions, flying aircraft built by furniture makers and piano craftsmen against the most heavily defended targets in Europe. And then the missions got genuinely interesting. The Office of Strategic Services, the OSS, America's wartime intelligence agency, predecessor to the CIA, needed a capability that no conventional aircraft could provide. They needed to communicate with agents on the ground in occupied Europe, not through dead drops that might be discovered, not through coded radio transmissions that could be detected and triangulated by German direction-finding equipment. They needed direct voice communication, real-time conversations with operatives working behind enemy lines. The technology they developed was called the Joan-Eleanor system, and it represented a remarkable achievement in wartime communications engineering. The agent on the ground carried a small handheld transceiver, about the size of a thick book, concealable in a coat pocket. This was the Joan unit, named with the casual informality that characterized OSS operations. The Eleanor unit was aircraft-mounted, a more sophisticated system capable of receiving the weak ground transmission and responding with clear audio. The operating principle was elegantly simple. Radio transmissions travel in straight lines. A transmission aimed upward, toward an aircraft directly overhead, would be extremely difficult for ground-based German detection equipment to intercept, because the signal wasn't traveling horizontally where it could be picked up by direction-finding stations. The agent could transmit detailed reports, spoken intelligence, rather than the laboriously encoded Morse that conventional spy radios required, while the aircraft circled above, invisible at high altitude, receiving everything and responding with instructions, questions, and coordination. The system required an aircraft that could reach occupied territory, loiter at high altitude without being intercepted, and return safely. Speed mattered, to get there and back through defended airspace. Altitude mattered, to avoid detection and interception. Range mattered. Some agents were operating deep inside the Reich itself. The aircraft they chose for these missions was the Mosquito. American intelligence operatives, conducting some of the most sensitive missions of the war, were flying in British wooden aircraft that American manufacturers had unanimously rejected. The same nation that had dismissed the Mosquito as plywood and glue desperation was entrusting its most classified intelligence operations to that exact aircraft. OSS crews would fly their Mosquitoes over occupied Europe at night, climbing to altitudes where interception was nearly impossible, and circle above their agents while information flowed in both directions. The pilots navigated with precision to coordinates that corresponded to isolated fields or forest clearings, where agents waited with their Joan units. The communications operators worked the Eleanor equipment, recording transmissions, responding with instructions, confirming that the agent was still alive and still operational. These weren't combat missions in the conventional sense. They were something more delicate, maintaining human connections across enemy territory, coordinating networks of operatives whose lives depended on the aircraft's ability to reach them and return undetected. An agent whose Joan Eleanor contact failed to appear would know that something had gone wrong, that the aircraft had been intercepted, or mechanical failure had forced an abort, or the mission had been cancelled for reasons the agent might never learn. Every successful contact confirmed not just the passage of information, but the continued functioning of the entire network. The Joan Eleanor missions demonstrated capabilities that the 1940 rejection letters hadn't contemplated. Beechcraft had worried about serviceability and ease of construction. OSS mission planners cared about performance at altitude and reliability over distance. Curtiss Wright had questioned structural strength. OSS crews cared about whether the aircraft could get them home from missions hundreds of miles inside enemy territory. The criteria that mattered in actual operations bore little relationship to the criteria that American manufacturers had used to condemn the design. Let me put the performance in perspective. The P-38 Lightning, the aircraft that American officials had believed would handle anything the Mosquito could do, was certainly capable in multiple roles. But consider the specific demands of photo reconnaissance work over heavily defended targets. A photo reconnaissance aircraft needs to reach the target, photograph it accurately, and return with the photographs intact. Speed matters because faster aircraft spend less time over defended territory. Altitude matters because higher aircraft are harder to intercept and harder to hit with flak. Range matters because important targets are often deep inside enemy territory. The Mosquito PR Mark 16 could reach 38,000 feet and cruise at over 400 miles per hour. It could photograph Berlin, Vienna, and targets throughout occupied Europe that other reconnaissance aircraft couldn't reach. When Roosevelt flew a Mosquito PR Mark IV for combat evaluation in 1944, he discovered that it outperformed the F-4s, reconnaissance P-38s, that his unit had been operating. The aircraft didn't just match American alternatives, it exceeded them. In the specific mission that American intelligence services needed performed, the rejected British design was demonstrably superior to the American aircraft that had been deemed acceptable. The same pattern held across multiple applications. Light bombers? The Mosquito carried 4,000 pounds of bombs, including the 4,000-pound Cookie blockbuster, to targets in Germany, while flying fast enough to survive without defensive armament. American light bombers like the Douglas A-20 Havoc and the later Martin B-26 Marauder were slower, required defensive gunners and their associated weight, and suffered higher loss rates over comparable targets. Night fighters? The Mosquito night fighter variants combined radar, speed, and heavy armament in a package that proved devastatingly effective against German night raiders. American night fighters existed, but they achieved nothing comparable in the night defense of Britain. Precision attack? The Mosquito's combination of speed, accuracy, and bomb load enabled precision raids. Amiens Prison, Gestapo headquarters in Copenhagen and The Hague, the Shell House building in Copenhagen, and dozens of other precision targets that no American aircraft in the theatre could have executed. Anti-shipping? The Tsetsi, with its 57mm cannon, represented a capability that existed nowhere else in any air force. No American aircraft hunted submarines with anti-tank guns. The evidence was overwhelming and undeniable. The rejected aircraft outperformed American alternatives in role after role, mission after mission, target after target. Here's the part that rarely receives attention in American-dominated histories of the war. The Mosquito's success was not merely a British achievement. It was a Commonwealth achievement, a demonstration of industrial cooperation across nations that shared engineering traditions and strategic objectives. De Havilland Canada at Downsview produced over 1,000 aircraft. De Havilland Australia in Sydney added to the total. British factories from Hatfield to Leavesden to Broughton turned out aircraft at rates that surprised skeptics who had doubted wooden construction could achieve meaningful production volumes. The workforce that built Mosquitoes looked nothing like the workforce that built American bombers. Furniture factories were converted to aircraft production. Piano makers applied their woodworking expertise to military aviation. Craftsmen who had spent their careers working with veneers and laminates and precision joinery discovered that their skills transferred directly to aircraft construction. No aluminium shortage could constrain them. They weren't competing for the same materials as Spitfire and Lancaster production. No metalworking expertise was required. They drew on entirely different skills. The labour force that built metal aircraft remained available for metal aircraft, while a parallel industrial base produced Mosquitoes from materials and skills that would otherwise have sat idle. That was the strategic genius that American manufacturers had missed entirely. Geoffrey de Havilland hadn't chosen wood because Britain couldn't afford aluminium. He'd chosen wood because Britain had woodworkers who weren't building anything else. He'd identified an unused industrial capacity and designed an aircraft to exploit it. The Mosquito didn't compete with metal aircraft for resources. It supplemented them. 7,778 Mosquitoes. That's the final production figure across all Commonwealth manufacturers. Built across 4 years of war by an industrial base that metal aircraft production couldn't tap. If that capacity had been devoted to aluminium construction instead, it would have competed directly with Spitfire and Lancaster and Halifax production for materials and workers. Instead, Britain got both. Heavy bombers and fast bombers, defensive fighters and offensive fighter bombers. The American manufacturers who wrote those rejection letters were answering the wrong question. They evaluated wood against metal in abstract terms and found wood wanting. They never considered whether an all-metal Mosquito equivalent could have been produced at all, given competing demands for aluminium and skilled metalworkers. They never considered that an aircraft's strategic value depends not just on its performance specifications, but on whether it can be built in useful numbers without disrupting other essential programs. They applied peacetime evaluation criteria to a total war problem, and they got the answer catastrophically wrong. The reversal that followed Pearl Harbor was not simply a change in American procurement policy. It was an admission, quietly, implicitly, but unmistakably, that the institutional certainty of 1941 had been institutional arrogance. The rejection letters remain in the archives. Beechcraft's assessment declaring wooden construction unsuitable for efficient aircraft. Curtiss Wright's dismissal. Fairchild's rejection, Fleetwing's refusal, Hughes' condemnation. 5 documents written with absolute confidence by experts who believed they were stating obvious truths. The reverse Lend-Lease records remain in the archives too. 120 mosquitoes, requested by the same nation whose manufacturers had declared the design unsuitable. Aircraft purchased through a program that reversed the normal flow of war materials, Britain supplying America rather than the usual arrangement. The receipts exist. The documentation is preserved. The evidence is there for anyone who cares to examine it. American manufacturers told the British their aircraft was unsuitable for efficient construction. Then American crews flew that aircraft on missions that required the most capable platform available. The contradiction isn't subtle. The reversal isn't ambiguous. What lessons emerged from this episode? The most obvious lesson concerns the danger of institutional arrogance, the tendency of experts to dismiss unfamiliar approaches simply because they are unfamiliar. The American manufacturers who rejected the mosquito were not stupid men. They possessed genuine expertise in aircraft design and construction, but their expertise had calcified into orthodoxy. They knew that metal was the modern material for aircraft construction. They knew that wooden construction was primitive, a step backward, a concession to desperation. They knew these things with such certainty that contrary evidence couldn't penetrate their conviction. General Arnold had seen the aircraft perform. He'd watched it execute maneuvers that demonstrated exceptional capability. But his observations couldn't overcome the weight of expert opinion. The manufacturers had spoken. The generals had to listen. A second lesson concerns the importance of matching solutions to specific circumstances. The mosquito succeeded not despite its wooden construction, but in significant measure because of it. Wood made the aircraft lighter. Wood enabled production using labour that would otherwise have been idle. Wood freed aluminium for other programs. Wood solved problems that metal would have created. The American manufacturers evaluated wood as though the only question was, is wood as good as metal in the abstract? The relevant question was, can a wooden aircraft meet operational requirements while being produced in useful numbers without disrupting other programs? They asked the wrong question and reached the wrong answer. A third lesson concerns the value of persistence in the face of expert dismissal. Geoffrey de Havilland believed in his design. The British Air Ministry, despite its own reservations, funded the prototype. The RAF, despite institutional skepticism about unarmed bombers, found roles for the aircraft that emerged. At each stage, the Mosquito faced doubters who could have killed the program. At each stage, supporters found ways to keep the project alive long enough for results to speak. The American rejection could have ended the story. If de Havilland had been more dependent on American cooperation, if the RAF had been more susceptible to American opinion, if the British government had been more deferential to Allied assessments, the Mosquito might have been cancelled or marginalised, and the capabilities it demonstrated would never have emerged. But the British kept building. The Canadians kept building. The Australians kept building. And when American circumstances changed, when American requirements expanded, when American officials discovered they needed capabilities that their own programs couldn't provide, the aircraft they had rejected was there, proven in combat, available for procurement. The men who flew Mosquitoes understood what the manufacturers who rejected them did not. Flight lieutenants of RAF Coastal Command pressed their tsetse attacks through submarine flak because they trusted the aircraft to get them there and get them home. Squadron leaders of Pathfinder Force led marking runs over defended targets because the aircraft's speed gave them margins that slower designs couldn't match. Pilots of 2 Group executed precision raids at rooftop height because the aircraft's handling allowed maneuvers that heavier aircraft couldn't perform. These weren't men flying an aircraft of desperation. They were men flying an aircraft of excellence, an aircraft whose capabilities had been proven in conditions that no manufacturer's evaluation could replicate. The proof was in the missions flown, the targets photographed, the bombs delivered, the submarines sunk, the intelligence gathered. The proof accumulated day by day, sortie by sortie, across every theatre where the RAF and its Commonwealth partners fought. By 1945, no one was calling it plywood and glue anymore. No one was suggesting that wooden constructions sacrificed structural strength or flying characteristics. No one was claiming that the materials were unsuitable for efficient aircraft construction. The evidence had spoken too clearly for anyone to maintain those positions with a straight face. And in the final months of the war, American OSS crews were flying Mosquitoes over occupied Europe, circling in darkness above agents whose lives depended on the aircraft reaching them, trusting British wooden construction for missions so sensitive they remained classified for decades. The same Americans who had dismissed the aircraft as unsuitable were flying it for operations they couldn't trust to anything else. The irony landed. It lands still. They called it plywood and glue. They said it sacrificed structural strength. They insisted the materials were unsuitable for efficient aircraft. Then they flew it against Berlin. They flew it hunting submarines. They flew it on intelligence missions that shaped the final campaigns of the war. Geoffrey de Havilland's vision, a fast wooden bomber that would survive through speed rather than armament, had been vindicated not by argument but by performance. Not by debate but by results. Not by persuading the skeptics but by outlasting them. The Mosquito didn't need American approval to prove itself. It proved itself over occupied Europe and the Bay of Biscay and every theatre where Allied forces fought. It proved itself in production numbers that exceeded what critics had imagined possible. It proved itself in versatility that no other single design matched. The rejection letters of 1941 stand as monuments to expert certainty, documents that remind us how confidently experts can be wrong, how institutional orthodoxy can blind intelligent people to evidence, how the familiar can seem inherently superior to the unfamiliar simply because it is familiar. The reverse Lend-Lease orders of 1944 stand as monuments to humility, documents that record the quiet admission that the experts had been mistaken, that the rejected design had proven itself, that America needed what it had dismissed. 120 aircraft, requested through a program designed for the opposite purpose, purchased from a nation that America usually supplied rather than the reverse. That's the documented reversal. That's the receipt for American error. That's the vindication that the evidence demanded and circumstances extracted. The Mosquito flew until 1955 in RAF service, a remarkable operational lifespan for a design conceived before the Second World War began. Jet aircraft eventually replaced it, as jet aircraft replaced everything from the propeller era. But for 15 years, the plywood and glue aircraft served frontline squadrons in roles that its critics had declared it unsuitable to perform. The experts at Beech and Curtiss-Wright and Fairchild and Fleetwings and Hughes had been certain. They had been unanimous. They had been documented in their confidence. They had been wrong. And the records that prove they were wrong, the rejection letters and the procurement orders and the mission reports and the loss statistics, survive in archives on both sides of the Atlantic, waiting for anyone who cares to examine them. 18 months from dismissal to desperation. 18 months from unsuitable for efficient aircraft to send us as many as you can. 18 months from American confidence to American reversal. The Mosquito outlasted the experts who rejected it, outlasted the officials who believed the P-38 would handle anything Britain's wooden aircraft could accomplish. outlasted the institutional certainty that metal was the only proper material for modern military aviation. Built from birch plywood and balsa and casein glue by craftsmen who had spent their careers making furniture and pianos, the Mosquito became one of the most successful aircraft of the Second World War. And when American intelligence needed aircraft for their most sensitive missions, missions requiring speed and altitude and range and reliability, missions that would determine the fate of agents operating behind enemy lines, they didn't fly American designs built from American materials by American methods. They flew Mosquitoes. Subscribe for more stories like this.